As your mobile device is busy executing tasks, calculating how to split a bar tab, and uploading photos of your cat, the underlying hardware is effectively pulling energy from your battery to accomplish this work. And as we've all seen, the more work your device does, the more battery it pulls, and sooner rather than later, your users are left holding on to an uncharged phone that doubles as an expensive doorstop. The key to writing applications that are light on battery drain has everything to do with understanding how the process works under the hood. In the electrical engineering world, this action of a hardware pulling energy from the battery to execute tasks is called current draw over time. And anyone who has an undergraduate in electrical engineering will tell you not every action on your device draws the same amount of battery in the same way over the same period of time. To prove this, let's take a handy Nexus 5 device, turn it on airplane mode, and let it sit on our desk. If we leave the phone like this, doing nothing, we'll roughly get a month of life before the battery is completely exhausted. Feel free to try this one at home, kids. We can consider this the baseline in terms of battery life. But that's not really how these devices are typically used. As soon as you're active, you're going to be eating up more battery. Now, active in this context includes things like the CPU doing work, cellular radio transmitting data, and the screen itself being awake. So the question is this: what tasks are my application doing that's eating up the most battery? Sadly, though, that's not easy to answer. Monitoring battery drain at the hardware level is a catch-22 because, of course, the monitoring itself needs to drain battery to execute the actions to record how much battery is being drained. And as such, most mobile devices don't do this. The only real way to gather these types of statistics on battery draw is to attach a third-party piece of hardware to your Android device, which can record the operations without using up the phone's power to do so. Now, when we do this, we actually get some really interesting information. For example, when a Nexus 5 is in standby mode, there's actually not much power drain going on, right? But when we wake the device up or turn on the screen, we can see a huge power spike in the battery monitor, which, I mean, you'd kind of expect, right? Turning on LEDs, painting the screen, and then all that CPU, GPU work required to draw to the screen isn't free from a battery perspective, which, by the way, is completely different from when the application wakes up the device. Say if it's using Wake Lock, Alarm Manager, or the Job Scheduler API. When the device is asleep and it's woken up through one of these APIs, you'll see an initial battery spike as the processor first wakes up, followed by a bit of work as it's executed. Now, it's important to note that once the work is done, the device will go back to sleep on its own, which is really important. Keeping the device awake for long periods when doing little or no work will easily chew up your battery life. Now, your cellular radio, on the other hand, is a completely different beast in this regard. When your device tries to send data over the mobile network, you can see that there's a quick wake-up cost associated with getting your mobile hardware ready, followed by a large spike for sending out a data packet, and then another large spike for receiving one back. And because getting the radio started is so expensive, after it's done executing work, it will stay on in a wait state for a short period of time in case there are more packets ready to come in right away. So all this is great data, but most developers don't have access to this kind of equipment, right? I mean, but with the L release of Android, we've got a whole new set of tools to help you optimize the battery draw of your application. Let's take a deeper look at Battery Historian.